Where are we? Here we are. Okay, 72. Okay, 72. So we have this given function. Is this in our traditional exponential form or our continuous rate form? Like traditional exponential or continuous rate form? Or old school, right? The one we started with, a, b to the t. So it first asks for the annual percent change. So we got a, b to the t, and that is 10 times 0.71 to the t. In my worst writing. Okay, so what's the annual percent change? Annual percent change, how are we going to find that? Yeah? So you're saying that the value of b is 0.71?
No, it's 29%. The annual percent change.
But b isn't the annual percent change. What is b? B is the decay factor, right? The multiplier. So you're right that the percent change is going to be... So what is the percent change? 29%? Not quite. Yes, it's asking for percent change. Then we want negative 29%. And that comes from a decay factor of 0.71, which is what? The multiplier on output that gives us the next output. This whole module is about these growth factors and decay factors. So this is decay factor, the multiplier on output that gives us the next output. Therefore, the 0.71 represents what about the what? Output. What does 0.71 represent about the output? Yeah. Percentage left over, the percentage retained, or the percentage we keep, right? So it's what we keep every unit of input. Therefore, we're losing 29%. Okay, so now they want us to change it into this form, a e to the kt. So we want to change that into a e to the kt. And so what is the key to this? How are we going to change this a? What do we need? We need k. What is a? A is still 10. That doesn't change. The t is our inputs, the same. So what's left is e to the k, or just k. We know that e is a value. So how are we going to get k? E to the k equals?
0. minus 0.29.
This is the key. So the key is that you know that b is e to the k, and that you're very, very sure about what all these numbers are. B. Does it reflect true percent decrease or not? B. Does it reflect the true percent decrease or not? B. Yes, it's the true decay factor. So it reflects the true percent decrease. B. It's the true decay factor. It's 0.71, and our percent decrease is 29%. That's what B is. What about K? First of all, is it a decay factor or a rate? It's a rate. Is that rate the percent decrease per unit? K?
Yes.
No.
Okay.
That's the continuous rate. That is not the true percent decrease. The true percent decrease comes from B, the true decay factor. Is it better? B is the true growth or decay factor. It gives the true percent increase. K is the continuous rate, which is like an APR, right? It has to be combined with continuous compounding, and then it results in the true percent change. So we know our b. What is our b? 0.71, and with it we can find k. So how in the world are we going to get this value of k? What's that? Natural log. Because natural logs are what? What is a natural log? It's an yeah. So if we want an exponent, we're going to write it as a log. So which exponent do we have? We have the exponent of e. That gives 0.71. This is the exponent of e that gives 0.71, and so that it would be the exponent of e, running out of space, that gives 0.71. I'm going to try it again. The exponent of e that gives 0.71. That's better. And what are exponents of e? Natural log. Log base e is natural log. What do we say? Every natural log is an exponent of e. It's the exponent of e that gives this number right here. That's what a natural log is. That's an exponent of e. Okay, what is ln of 0.71? Negative 0.342 or negative 34.2%. Okay, so question. There's a rate, there's a rate. Okay, that's K. And that's the percent change. Are these rates the same or different? Are these rates the same or different? Negative 29% and a continuous rate of negative 34.2%. Are they the same or different? Answer up in the ceiling there? What do you think?
They're the same, but one's percentage and one is decimal form.
Oh no, they're both in percent form. This is 34.2% and this is 29%.
Oh, I thought we were talking about
They're not the same.
They're not the same because we have to do something with e.
Because we have to do something with e. So everyone agrees they're not the same?
I think they're,
What's that?
so I think they're equal.
How are they equal?
E to the k is a reflection, or not a reflection, it's equal to b. So they're going to be equal values. But if one is a continuous rate and one is just a compounded rate.
But k on its own is not equal to your e.
That's right.
Are we talking about e to the k?
Or just k.
K. I thought we were talking about e to the k.
I'm comparing these two numbers. Negative 34.2% and negative 29%. Those are both percents. Are they the same or are they different? Obviously they're different numbers, right? So that's not what I'm asking. I know that 34.2 is a different number than 29, obviously. I'm a math teacher, okay? So what is my question really? Do they represent the same growth or decay? Do they represent the same decay or different patterns of decay? Jaden.
Yes, because e to the k is the same as b.
What's that?
E to the k equals b.
Okay.
And if you put it back in a times b to the c form, it's still going to be the same.
Okay, so you're arguing through kind of the calculations, that they're the same by the calculations.
Yeah.
But are they the same pattern of decay? Do they represent the same pattern of decay or not? So if I had a graph like this, and this is what? This is some, who knows what this is, some population, okay? And it's going down like this, right? So we know it's decay. So this is 1, 2, 3. And after 1 unit of t, we'll get some output. And after 2 units of t, we'll have some output. And after 3 units of t, we'll have some output. will those ordered pairs, those results of output for 1, 2, and 3, be the same or different for these two values? Same or different? So Jaden was saying, those are equal, right? Yeah, it's just two different perspectives on the exact same decay. It's two different perspectives on the exact same decay. A true percent decrease of 29% every unit, or a continuous rate of 34.2%. Remember that the APR did not reflect the true percent change. And so with an APR of 12%, that wasn't your true increase on your money. Remember? Just the same thing like this. The continuous rate is not the true reflection of how much it goes down. How much does it go down? It truly goes down 29% per unit.
So are they the same or not? Right now you were asking if they were the same.
Yes.
So
Are they the same pattern of decay? Absolutely. They will both give the exact same outputs for the same inputs. Yeah, Nina.
Even for numbers that aren't whole units?
Yeah, sure. 1.5, 0.5, 2.5, because it's because AB to the T is equal to AE to the KT.
So it's just a different way of representing.
It's a different perspective on the exact same function, right? It's a different perspective on the exact same function, whether you look at it through the eyes of B or you look at it through the eyes of K.
So what's the significance of having two different ways to say it, like the continuous one? Why is it important to be able to express it like that?
Because you're expressing it through the idea of continuous compounding. We're saying what percent, if it was compounded every single moment, would result in a true percent change of 29, and that's what it is, 34.2. So if you keep adding in your tiny bits of decrease, you keep subtracting moment by moment over the course of 1 unit, then 34.2% continuous will result in a true decrease of 29%. But they're just two perspectives on the same thing. So it's really crucial that when you see this, the E and the K and the B, you know exactly what everything means. Why? Because we end up getting two different percents that represent the same relationship. So you got to know what K is, and you got to know what B is. So go ahead, Alex.
is one more accurate than the other if you're
No.
trying to represent a situation?
No, they're the same. So the only time one would be more accurate is if in finding one from the other you rounded. So we probably rounded this a little bit. It's 34.2. Maybe it was a 34.25 or something. So we know that this is exactly correct, 29%, because of the 0.71. In finding this, if we rounded, then it's slightly off. Yeah. Other questions? Okay. What was the other one? 78. So the population increased by 2.1% per year. The population increased by 2.1% per year. Are they giving us something that will that ties in closely to B, or are they giving us K? Are they giving us what we could use to find B, or are they giving us K? So the key is, does it say continuous rate? No. It says the population increased by this much. Therefore, what can we conclude? No. No, this is the true increase percent. Therefore, we can say that B equals 1.021. A true increase of 2.1% means a growth factor of 1.021. Okay, so we can write then, starting in 2003, 292,430, 1.021 to the T. Now we want to rewrite it in e to the k, a e to the k form. So this is equal to, exact same function, just written a different way. E to the kt. So therefore, again, b equals e to the k. B is the true growth factor, representing the true percent change. K is the continuous rate. What exponent is k? K is the exponent of e that gives exponents of e are natural logs. Find it. What's the natural log of 1.021? 0.02078. Therefore, the continuous rate is compared to 2.1%. Which one is the true percent increase? 2.1 or 2.078? 2.1 is the true increase that was given. 2.078 is K. It's like an APR. It's like an APR. It needs to be combined with a continuous compounding to get your true rate of increase. We didn't do D, so don't worry about D. We didn't get to that, so hopefully you didn't spend too much time on that. Sorry. Okay, other questions on the homework or this stuff? Okay, so here's kind of a review quiz for all the modules. So it includes recent stuff as well as previous stuff. We have about 10 minutes to finish it. You can have something to write with and a calculator. Okay, so in first class, A was the difficulty because it was kind of review. It was kind of from like a week or two ago. So you got to make sure you get A right. Show all your work. Write out all your work when you do this. Sure. There's no internet. You're fine. Hand them in to Megan. Yeah, just pass it in. You don't have to stick it up. Okay, so I'll just do part A. Parts B through D are kind of just what you got finished doing and what we just did now, so I'll just do part A. So if this is exponential growth, then what characterizes exponential growth? Multipliers, right? Multipliers on output to get another output. So which growth factor would that be? The 4-hour growth factor would be the multiplier on 8 that would give you 14. The multiplier on 8 that would give you 14, which would be 14 over 8, 1.75. So 1.75 is the multiplier on your output at 0 that would give you your output at 4, so that's the 4-hour growth factor. If you want the percent increase per hour, then you need the 1-hour growth factor, which would be 1.75 to the 1/4. And I think you get 1.01502. Do I remember that correctly? So what's the percent increase every hour? 1.15, thank you. Sorry, I didn't mean to scare you, those who got it right. Is that better? Therefore, percent increase? 15.02% per hour. True increase? It's not the continuous rate. That's the true percent increase because it came from our true 1-hour growth factor, 1.1502. So then our A-B form would be the 8 times 1.1502 to the x, or h, equals f of h. So remember, exponential growth is so as we wrap this up, it's a very specific type of growth. It's not just a curve. If you see a curve, that's not necessarily exponential growth. It has to have this thing where you have a multiplier on output that gives you another output, and that stays the same. It's a constant. So what would we do to get the depth at 8 hours? The depth at 8 hours would be 14 times 1.75. If we took 14 times 1.75, that would give us the depth at 8 hours, right? 4 hours later. That's how things grow exponentially, okay? It's not just any curve means exponential growth. Okay, so that's, we're wrapping up Module 4, and we'll start Module 5. Our exam is the Thursday after break. So we have Thursday this week, Tuesday after break, and then the exam. Okay, so we're going to start Module 5. We'll spend the rest of these classes before the test on Module 5, and then the exam will cover Modules 4 and 5. Okay? Module 5 is a lot shorter.
I have a question.
Please.
Will we have 2 days to do it before, or will it be in class?
I think I scheduled it. No, it's not in class. Yeah, it'll be in the testing center. I'm pretty sure I scheduled it for 2 days, yeah. Wednesday and Thursday. Okay, so did we ever talk about this word? Ever, like toward the beginning of the semester, did I ever mention this word? I did? Oh, it was in their homework? Okay. So what I said was at the beginning that the it wouldn't be wrong to say that this class is about quantities. And then we went on to say that we could build on that. We could say this class is about changing quantities. Okay, changing quantities. Well, then we could even go a step further and say that this class is all about this, covariation. So what do you suppose that word kind of is? It's very well chosen. So what do you suppose that word means? Somebody knew. What do you suppose covariation means? We just got done saying this course is about changing quantities. How could we add another layer to that and say this course is about covariation? Okay, Jaden, go ahead.
Quantities change together.
What's that?
Quantities change.
He said how quantities change together. Is that what you're going to say? Yeah, so now we have two changing quantities, and it's how they change together. How they change together. And that's really what we've been doing so far. So everything we've done so far has been about that. We could say proportionality is how do x and y change together? They change together such that the ratio of the two quantities is constant. Y over x equals k. That's proportionality. That's a way in which two quantities change together. Okay, we talked a lot about constant rate of change. And we said, how do those two quantities change together? Well, we said changes in y, the ratio of changes in y to changes in x stays constant. That's constant rate of change. Or we said, for every equal change in x, what happens? For every equal change in x, we get consistent changes in y, right? That's constant rate of change, and that's a very specific way that two quantities can change together. And then we just got done with 2 or 3 weeks of exponential growth. And what happens with exponential growth? So as x increases one at a time, we have a constant multiplier from one output between the outputs, right? So as x increases 1 unit at a time, we always multiply by the same 1 unit growth factor. So y next over y current is this value b. Okay, so we've really spent most of our time on constant rate of change and exponential growth. But so now we want to just talk about covariation kind of more in general without putting actual numbers on it, and just say how could we model any two quantities? How could we create a graph that shows how two quantities change together? All right, so here's a very specific kind of method I want to teach you. And at first you kind of have to memorize this, and you have to say, okay, what's step 1, step 2, step 3? But then the end goal is that you can just be fluent in communicating about a situation, okay? That you're not tied to these rules. But at first we have to practice this to get the hang of it. Okay, so first thing we want to do is we want to identify which quantity should be independent. That's like our input. And the other dependent, like our output. And usually we use x to be the independent variable and y to be the dependent. But that's just, convention, which doesn't, it's not necessarily have to be true. Okay? And then here's what we're going to do first. So we're going to consider small equal increases of the first quantity. Small equal increases of our x quantity, or our input quantity, or our independent quantity. So this is the key to this part. This is the setup. Okay, this is the setup. And as we do that, we're going to ask questions about the other quantity. So you see, we're talking about changing the first quantity, making small equal increments of the first quantity, and seeing what happens to the other quantity. Right? So that's the idea of covariation. That's the idea, how are they changing together? So the first thing we'll ask is the most obvious question. As we make these changes in x, what does y do? Does it increase or does it decrease? Does it stay the same? So a very basic question to start out with. Okay? Then we get more technical, or we get more kind of demanding here as to what's going on, and we say, as x increases, how does the current change in y compare to the previous change in y? In other words, how are the changes in y changing? How are the changes in y changing? So here's where we're getting into the kind of the real nuts and bolts of how these two quantities are changing together. when we compare changes, successive changes of the second quantity as we let the first quantity increase. And then, so this is kind of the most important step. And this is the one you'll be the most resistant to, because you've never done anything like, most of you have never done anything like this before. Okay? But it's the most important thing. So your tendency is just going to be to stream, or to fast track right to generalizations. You just want to look at the big picture and tell me what the answer is. It's not what we're about. So we want to practice one change at a time, getting the resulting change in y and comparing those changes. So this will take a very deliberate act on your part to catch yourself not doing this and doing something else where you're trying to come up with the answer really quickly. Okay. From that comes, how does the rate of change change? So this is a direct result. The way that the changes in y are changing then determines how the rate of change is changing. How the rate of change is changing. So we want to focus on B. If we can get B right, then C just falls into place. Okay? C is no problem. Okay, so when we're first doing these examples today in class and Thursday in class and in your homework, you should have this roadmap with you on the side, and force yourself to stick to this roadmap. Okay? We need to practice, because then when examples get harder, so we're going to do easy examples at first, but when the examples get harder and you start just generalizing right off the bat, that's when students make big errors and their judgments are wrong. But if you would slow down and actually take it step by step, practicing this, then you can truly understand how those two quantities are changing together. Okay. So let's try the first example we want to try is in your book on page so module 5, investigation 1, I think. Let's try this. Yep, very first one. So we're going to do number 1 together. So we're going to imagine a bottle looks like this, and we're going to put water in it, and then, of course, the result of putting water in it will be that the height of water changes in the bottle. So what is our independent and what is our dependent quantity? So what is our independent or input quantity here? We've got two possibilities: height of the water in the bottle or volume of the water in the bottle. What is our independent quantity or input quantity? Most people are saying volume. That's right, okay? And so normally, not necessarily, but normally we'll put the independent or input quantity on the horizontal axis. That's the most common use of a horizontal axis, is to put independent or input quantity. But that's not, it can be valid otherwise, right? So you can have other situations where it's valid, so that's not the case. But normally that's how we do it. And then, therefore, our dependent quantity is the height of water in the bottle. That should make sense, right? That should make sense, that depending on how much water you put in, we'll get a certain height of water in the bottle. So we've got our independent or input quantities. So this is input. What was the next thing we're going to do? And this is our output, dependent. What was the next thing we wanted to do? What's our strategy here? So we've figured out what's dependent and what's independent. Yes, Alex?
So you had the dependent variable or your output changes in response to changes in your input.
Right, and so that's a very broad statement. We want to do that in a very, very strategic way. So what's the first step in doing that? It's the first thing we're going to look at. Increase x by a small amount, right? Exactly. So I'm going to choose my small amounts to be these grid lines. Okay? Maybe it's an ounce at a time. Maybe it's an ounce at a time. So, and we can call that change, that first change in volume, I can call it, like, say, delta V1, right? It's my first little change of volume. And what's going to happen? So we're going to put an ounce of water in, or a half an ounce, or whatever the small amount of water is in, and how is the height, this quantity of height, going to be changed? What's going to happen? It's going to increase, right? So we're going to get an increase in the height. A big increase or small increase? What do you think? For an ounce, are we going to get half the bottle filled up? No, it's just going to be a little bit of increase, right? So we can come down here and we can just kind of, the numbers don't matter at this point, it's just relative sizes. Okay, so I can represent that little bit of change in height, and I can call that delta H1. And that gives us a point, right? That gives us a corresponding volume and height. Right there. Okay, what do we do next? Patrick? Good, excellent. So we're going to put the same amount of water in again. We'll call it delta V2, but it's equal to delta V1, right? And I'm using the vertical lines to mark off my delta V. So that's delta V2 equal to delta V1. Okay, and so what's going to happen to the height? It's going to stay the same or decrease or increase? Increase. Okay, so now we go to the second question. The amount of increase, that change, how does it compare to the amount of increase of the first one? I heard the same and bigger. Taz, why bigger?
Because the size of the base is going to be coming in, so it's going to fill up more of it.
He says because the sides are getting narrower, it's going to fill up more. The height's going to increase more than it did before. You're going to change and go with that?
Yeah.
Yeah. So now our delta H2 is going to be a little bit more than delta H1. So I'm trying to show that just a little bit greater than this one. This is our delta H2. And we're saying that's greater than delta H1 because of the sides getting narrower. Gives us another point on the graph. Okay, what's next? Good, another equal amount of water. Small equal increments of water. And then we're going to get a resulting change in height. Will the change be negative, 0, or positive? Positive. And how will it compare to the previous change? Slightly larger again. Delta H3, which will be greater than delta H2. Gives us another point. We'll do one more. So equal increase in volume. How will this change in height compare to the previous? Less, the same, or more? Larger. Gives us another point. So this is called incremental thinking. Incremental thinking means we think small changes at a time of the independent or the input variable, and we compare the resulting changes of the output. So now we can generalize and say, here are the changes in height. First of all, the changes in height, are they positive or negative? They're positive changes. The height is going up. The height is going up, and that's obvious when you add water to the bottle. And so those are positive changes, and are those changes, are they decreasing, staying the same, or increasing? And these are increasing changes. So the height is increasing, and the changes are increasing. Okay? So now, for equal changes in input, we're getting increasing changes in output. Is this constant rate of change? If it were constant rate of change, what would be happening? For equal changes in input, we would get Consistent changes in output. Remember we talked about that. So we're not getting consistent change. We're getting a larger change every time. Therefore, it's not constant rate of change. So therefore, what is it? Is it exponential? It's exponential growth because it's curved, right? No. It's just not constant rate of change. So it's not linear. It's curved, right? It's curved. But it's not, you don't conclude that it's exponential, right? Exponential is a very specific type of growth where you have what? Multipliers on output to get future outputs, right? You have a multiplier on output, always gives you the next output. So this is, we don't know. All we know is it's not constant, and therefore you get a curve. You get a curve. Okay, so I felt like you guys were with me in terms of really doing this one increment at a time, and that's what we want to practice. Even on easy examples, just practice the language. Practice going through equal small changes of input, comparing the resulting changes in output. So this time I'm going to draw you a graph, and then you're going to do this analysis. This is the important part. And then once you've feel like you've exhausted, talking about comparing changes, then draw the bottle at the very end, okay? So after 30 seconds, you shouldn't be drawing the bottle, okay? You're talking through the changes. So I'm first going to draw you the graph. Okay, so there's really 3 parts to this bottle. So you can break it up by part. So we can have part 1, part 2, part 3. So you're going to still follow the same 3 steps, and I'll erase this bottle in a second here. Still force yourself to do one small change at a time and analyze the resulting changes in height, doing it one small change at a time. And don't start even thinking about the bottle until you've done several successive changes, okay? And definitely get a partner and practice talking this out. But I'm just delineating 3 parts of the bottle. The dotted line is I'm just marking off 3 different parts of the bottle. So, okay, so take your time. Section 1 should take a couple minutes. Section 2, a couple minutes. Section 3, a couple minutes. You're talking about the changes, okay?
So section 1 is one whole fill, right?
No. Within section 1, you're going to do small changes. Yeah. Within section 1, you're going to have many small changes. Within section 2, I'm glad you asked that. Many small changes. So this time I'll make them like half a square each. Okay, so I'm kind of giving you some help there, marking out small changes in blue. So I want to hear you, as I come around, I want to hear you talking about changes in height and how they compare to previous changes in height. How does the current change in height compare to the previous change in height? Yep.
Would you say section 2 is a strike?
I'm trying to, yes.
Do you have a problem like that? So what's that answer? Didn't happen in the first part? You think the price is increasing? The first part, the rate is increasing. The price is increasing. Really? Height? When you put more water in the bottle, does the height increase? I put more water in the bottle, does the height ever not increase? Height always change. Okay, so the second part of the bottle, you want to talk about the changes in it. Is it change in height? Increasing. You guys agree with that, right? The changes in height increasing in the second part of the bottle. The changes are increasing. I asked in the second part of the bottle, the changes in height in the second part of the bottle is increasing. No. But those changes in the second part of the bottle are consistent, but compared to the changes in the first part of the bottle, it's prohibited.
Okay, so Anna, in the first part of the bottle, and just in part one, let's talk about the height first. So the height, is it decreasing, staying the same, or increasing? The height. The height is increasing. Okay. What about the changes in height? So I'm asking about the changes in height. So you're saying they stay the same. So she's saying that the changes in height are staying the same in the first part of the bottle. Would you agree with that? The changes in height in the first part of the bottle are staying the same for equal increments of volume. Right. And so what can you conclude then about this?
The bottle has to be the same size.
Okay. What kind of covariation do we have? What kind of covariation do we have? Constant rate of change, right? Because equal changes in volume are resulting in consistent changes in height. That's constant rate of change. We worked hard on that, right? And so now the bottle. You're saying the bottle is what? Boxy. Can you be more specific? So narrow boxy or wide boxy? What's that?
Wide,
Wider?
wider, straight sides.
Why? Why wider?
Because the height is increasing in such a small amount that no matter how much volume you add, it's not going to show a lot.
So she's saying that these changes although they're equal, they're small. The changes in height are smaller, which would mean a wider bottle, right? Cool. Okay, so what happens at the break point between 1 and 2? Somebody knew? Brian. So from 1 to 2, so let's just talk about 2 first. Can you talk about the changes of height in part 2?
They're greater than the changes in part
Greater than the change in part 1, but then what about just successively in there?
where the equal changes in x is
So in this part of the bottle, you're saying the changes in height are, say it again?
greater than the changes in x.
Okay, but just in this part of the bottle, what about the changes in height? Do they decrease? Do they stay the same, or they increase?
They stay the same.
They stay the same. So what kind of covariation do we have in the second part of the bottle?
Constant.
Constant rate of change, right? Constant rate of change again. But you're saying that those changes are a lot greater than the changes, the height changes that we got in the first part. Okay? So, what does that mean for the bottle?
It's narrow.
Narrower. And so does it kind of gradually get narrower? Suddenly. Why suddenly?
Because it's a straight increase.
Yeah, so in part 1, we have a certain rate of change, right? And then does that rate of change gradually or sharply? Yeah, there's like an actual sharp point on the graph. Suddenly, the rate is greater, so therefore, suddenly, the bottle is narrower. You don't have a bottle like this? Has everyone had a bottle like this? Okay, bring it on Thursday. Okay, last part. So here we go. Christina, how'd you do in the last part? Can you talk about the changes in height in the last part of the bottle? What's that? Increasing changes. So here's, say, I'll go by full squares. So here's in the third part, here's delta H1. Here's delta H2. Delta H3. And delta H4. So are those positive or negative changes in height, first of all? Christina, positive or negative changes? Positive changes, right? Height is increasing. The height itself is increasing. Okay? So now what about those changes? So the change in height is represented by this vertical line. So what do you think? So let's actually show these points. Am I adding points to the graph? Just highlighting, right? I'm just highlighting points that were already there. Okay, so our first change between this point and this point, the change in height is that vertical distance right there. Next change is the vertical distance between those 2 points. Next change, next change. So what about the changes in height? The changes in height. I'll try again. So is this change in height, is it greater than, the same as, or less than that change in height? Less. So the changes in height are doing what? Decreasing. The height, I said height changes Decreasing. So the height is increasing, but the changes in height are decreasing. Do you agree with that? Okay, so what shape of a bottle would result in, for equal increments of water, the change in the height would be getting less and less and less? What shape of bottle would that be? Draw it with your finger. Yeah, exactly. So getting wider like this, right? It's a wine glass that you can fill all the way to the bottom. And through the stem and into the bottom. Okay? Okay, so that is, the covariation stuff is a little bit easier when you have an increasing quantity. Our dependent quantity here is height. And so when that dependent quantity, in this case height, is increasing, it's an easier go. Okay, so let's try something a little bit more challenging. All right, any questions on this example? So again, the focus is, what is the height doing? What are changes in the height doing? Okay, so in the first part of the bottle, changes in the height were doing what? Staying constant. Second part of the bottle, changes in the height were constant again, but just bigger changes than the previous part. And then the third part of the bottle, changes were decreasing changes. Decreasing changes. Okay, so let's try. We can just use that graph. Okay, so we're going to do. Mark's going to make a fool of himself. Okay, here we go. So what we're gonna do is we're gonna look at an independent quantity of time and a dependent quantity of my distance from the chair. See the chair over there? So it's gonna be my distance from the chair, and we're going to, like I said, we're going to do independent quantity of time. So when I say go, that's time equals 0, and then we're just gonna let seconds go by, right? And then the dependent quantity is gonna be my distance from the chair. Okay, ready? So, ready, go. I'm not ashamed. Okay, so I'll do it again. Ready? So again, independent is time, dependent is distance from the chair. So, go. All right, so let's see if we can. No. You got it. You know what's going on. All right, so I'm just going to use the same graph. So therefore, what will go on the horizontal axis? Time. Time, since, remember, time is not a valid variable. So t equals time, what? Since I started to walk. Since starting to walk. And we'll do that seconds. All right, that's a well-defined variable. Time since starting to walk in seconds. And then this axis will be, what do we say? D is?
Distance from the chair.
Distance from the chair. Okay, and if it's a variable, so we could say feet, meters, doesn't matter, we'll say feet. We need some kind of variable. Okay, so we're going to just, you can ignore the bottle, it has nothing to do with the bottle. Okay, so at time equals 0, here I am, D equals 0, right? Let me put this point right down here, right? Time equals 0. Yeah, so it's not 0, right? At time equals 0, I started somewhere, some distance from the chair. So at time equals 0, I have some amount of positive distance from the chair. Okay? So we're going to let a little bit of time go by, say half a second. A half a second goes by. And what happened to my distance from the chair? Was it positive, negative, or 0? My distance, or sorry. What happened to my distance from the chair?
It It decreased.
Decreased. So did I have a positive or negative change? Negative change. Big negative change or a little negative change? I barely moved, right? But it is a negative change. So that gives us a point. Next half second. Was my change in distance from the chair, was it positive, negative, or 0?
Negative.
Had a negative change in distance because my distance went down, right? And how would you compare that to the previous change in distance? Slightly more negative or slightly less negative? Slightly more negative. Gives us another point. Next half second. Change in distance, positive or negative? Negative. Larger or smaller negative change than before? Larger. Okay, so what's happening? My changes in distance from the chair are negative, and are they getting more or less negative?
More negative.
They're getting more negative. So, changes from the chair, changes in distance are getting more negative. Are those increasing? Okay, don't pack up. Or at least listen very carefully. Are those increasing or decreasing changes? Are those increasing or decreasing changes?
They're getting more negative.
Are the changes getting more negative?
Yes.
And a sequence of values that get more negative, are those increasing or decreasing? Decreasing. This is very difficult. Students have a lot of trouble with this. The negatives are getting more negative. They're getting larger negatives. Okay? So these are negative changes. And they're getting what? More negative. What about the size of my changes in terms of this, the size of the distance I cover? Those are increasing. But because the quantity is distance from the chair, my distance, the change in distance from the chair is getting more negative, bigger negatives. Therefore, the changes are decreasing, not increasing. All right, so we get this concave down shape, which corresponds to decreasing changes. We're going to work hard on this, but it does not come easily. Okay, look online for homework. Okay, I'll post homework online.